Assalamualaikum and salam sejahtera. Hello everyone. Welcome back to my channel, Cikgu Hasnitah. So today, let us continue with our third content standard in Chapter 3, Gravitation, 3.3, Man-Made Satellite. So to begin our lesson, can you name me some example of man-made satellite which you know? Very good. Okay, as you can see in my bag, it is ISS International Space Station. And what about this? This is another example of man-made satellite which is called Miasat. Do you recognize the astronaut up there? Yes, that is our first space explorer, Dr. Sheikh Muzaffar Shah. So just now, I give you two examples of a man-made satellite, namely ISS, International Space Station, and Miasat. So this is the position of these two satellites on Earth orbit. Okay, ISS is about 408 kilometers from the center of the Earth, while Miasat is far, far away at a distance of 35,786 kilometers. So if you are ready and good to go, let us proceed with our first learning standard is to describe how an orbit of a satellite maintained at a specific height by setting the necessary satellite velocity. So are you ready to go? Very good. So let us check on this first activity is to determine the linear speed of a satellite. Remember linear speed we've learned before? Very good. Linear speed is the speed of an object when moving in circular motion. Yes, very good. And you are given with all this information. The mass of Earth is labeled with M, capital M. And the mass of satellite is given by small m. The radius of orbit of satellite is R. Alright, and then the linear speed of the satellite is given by V, and its orbital period is given by capital T. So how we are going to relate all this quantity? Let us check them together. So do you remember we've learned earlier centripetal force? Centripetal force is equal to the gravitational force between the sun and the planet, okay? Where in this equation, okay, on the left is the equation for centripetal force. Remember, F, centripetal force, equal to mv squared divided r. And on the right is the formula for, yes, very good, Newton universal law of gravitation, where F equal to g mm divided r squared. So if we equalize these two formula and we cancel all the common factor, so it will left us with v squared on the left and gm divided r on the right. And when we make v as the subject, so this is what we'll have. V equal to the square root of gm divided r. So this is the equation to determine linear speed of satellite. Alright? Okay, students. And if you look here, small r here refer to the radius of orbit. If the satellite is a few kilometer away or in a certain height from the Earth's surface, so this is how to determine the radius of orbit. You have to plus the radius of r with the height of the satellite from the Earth's surface. Okay, to understand this later, we'll see a few examples of questions. Did you experience the same problem with the man there? So let us take a look at the first example. Okay, we have a GPS, Global Positioning Satellite, which is orbiting the Earth. So you have to calculate the satellite linear speed if it is now at a height of 20,200 kilometers from the Earth, as shown in this diagram. So how to solve this? Okay, let's write them together. Okay, so first, students, remember how to solve a problem properly. First, you can extract or list out all the given information. So this is all the information from this question. So we want to find the linear speed. And this is your formula for linear speed. Okay, below here is the radius of Earth. So we have to plus the Earth radius plus the height of the satellite from the Earth surface. And second step, you just do the substitution with G. This is mass of Earth, radius of Earth, and the height of satellite. 2.02 times 10 power of 7. And then please work well with your calculator. So you will find this as the linear speed, 3.8713 times 10 to the power of 3 meter per second. Okay, who get the same answer with me? Very good. Okay, so this is the next question. Okay, can you think about this question? What will happen to the satellite if the linear speed of the satellite is less or more than the required linear speed? Okay, what happens if the linear speed is less than the required linear speed? Can you think? Very good. So what will happen? The satellite will fall to the lower orbit and continue to revolve towards the Earth until it enters the atmosphere. Okay? But now what if the linear speed is more than the required linear speed? What will happen then? Yes, very good. At this moment, the movement of the satellite at a higher linear speed against air resistance will generate heat and causes the satellite to burn, right? So it will cause a disaster. Okay, students, how do you think about the first learning standard? Easy, right? Okay, so now let us take a look at the second learning standard on to communicate about the geostationary and non-geostationary satellite. So what is the difference between these two types of satellite? So in this second activities, we are going to compare between geostationary satellite and a non-geostationary satellite. Okay, let us take a look at the characteristic for geostationary satellite first. Number 1, it is moved at a special orbit which is named the geostationary Earth orbit, GEO. Second, the geostationary satellite moves around the Earth in the same direction as the direction of the Earth rotation on its axis. Number 3, a geostationary satellite has an orbital period of 24 hours, which is same as the period of rotation of the Earth. And last but not least, a geostationary satellite is always above the same geographical location on Earth. Okay, then about a non-geostationary satellite. As you can see on the GIF there, it moves at a random direction. So number 1, a non-geostationary satellite normally locate in a lower or higher orbit than the geostationary Earth orbit, the GEO. Second, a non-geostationary satellite has an orbital period either shorter or longer than 24 hours. So if they are at a lower orbit, so yes, the orbital period will be shorter than 24 hours. And if they are at a higher orbit than the geostationary satellite, definitely their orbital period is longer than 24 hours. And the third characteristic, all non-geostationary satellite is above a different geographical location at different times. And this is the double bubble map that you can find in your textbook to compare and contrast geostationary satellite and non-geostationary satellite. Okay, let us take a look at the similarity first. So there are 3 similarities between these two types of satellite. The first one, both satellite orbits the Earth. Okay. Second, they both obey these equations of linear speed, where v, the linear speed of the satellite, equal to the square root of gm divide r, as we discussed in the first learning standard before. And they also obey this equation for the orbital period. Okay, the orbital period of the satellite is equal to the square root of 4 pi squared r cubed divide gm. Actually, this formula is the formula to determine the mass of planet we've learned in 3.2 before. In 3.1 before. And what about the example of satellite? We have communication satellite and Miasat satellite under geostationary type of satellite. And for non-geostationary satellite, we have Tiongsaat, Razaksat, PIPIT, ISS, the International Space Station, and all these satellite is for the purpose of Earth imaging, GPS, okay, weather forecast. And now we have come to the third and final learning standard is the conceptualize escape velocity. Any idea what is escape velocity refers to? Yes, escape velocity defined as the minimum velocity required or needed by who? By an object on the surface of the Earth for what? To overcome the gravitational force and to escape to the outer space. So how can an object achieve this escape velocity? So students, this escape velocity will be achieved when the minimum kinetic energy of an object is able to overcome the gravitational potential energy. So how to derive a formula for escape velocity? Let's take a look at this together. All right. Okay, so if you look in this figure, we have an Earth. Okay, and this is an object on the Earth surface. Okay, so an object is at a distance r. So this is the orbital radius from the center of the Earth. Okay, mass of object is given by small m, and mass of Earth is given by capital M. Okay, so this is the formula for kinetic energy. Any moving object possess kinetic energy. Yes, half mv squared kinetic energy. And for gravitational potential energy, it is given by this equation. Okay, negative g mm divide r, right? So remember, in order to achieve escape velocity, the minimum kinetic energy must be equal to the gravitational potential energy. So, according to the conservation of energy, okay, minimum kinetic energy plus gravitational potential energy will be 0. All right. Okay, so this is the equation for kinetic energy. This is the equation for gravitational potential energy. All right. Okay, so when we bring the gravitational potential energy to the right side, this is what we will have. Okay, and we cancel all the common factor of m. Okay, so it will leave us with v squared on the left. Okay, so we bring 2 at the other side. So v squared will be equal to 2gm divide r. Can you follow me so far? Very good. Okay, and finally, this is what we have. Make v as the subject. So v, escape velocity, equal to the square root of 2gm divide r. Easy, right? So we have derived the formula for escape velocity. So now let us practice how to apply this equation in order to solve a problem relates to escape velocity. Okay, for the first example, you are given this information. This is the Earth radius, the Earth mass, and this is gravitational constant. Okay, so how to find escape velocity from the Earth, students? So this is the formula. Then we do the substitution to this is g, m mass of Earth, and this is the Earth radius. So the answer is 11,181 meter per second, or in standard notation, 1.1181 times 10 power of 4 meter per second. So any object on the Earth's surface have to overcome this velocity in order to overcome the Earth's gravitational force and escape to the outer space. Understood? Very well. So I hope now you are clear how to determine escape velocity for an object on the Earth's surface or in any surface of a planet by applying the formula of V equal to the square root of 2gm divide r. And now let us take a look at this question. Why do you think the Earth can maintain a layer of atmosphere around it? Okay, so this is the value for high escape velocity we determined just now, 11,200 meter per second, approximately 11,200 meter per second. Okay, so if you relate this to the question, molecules in the atmosphere move at an average linear speed of 500 meter per second. That is very much lower compared to the escape velocity from the Earth. So what happened? A molecule that are moving randomly will not be able to escape from the Earth into the outer space. So they will linger around the Earth's surface. Clear? Yeah, very good. Okay, what about the second question? Commercial aircraft, why they cannot escape into the outer space? Commercial aircraft. So commercial aircraft, they are normally can fly at a linear speed of 240 meter per second, 250 meter per second. Again, this is very low compared to the Earth escape velocity of 11,200 meter per second. Same goes to a jet fighter, students. It can achieve a supersonic linear speed up to 2,200 meter per second. So still, both the linear speed are lower than the escape velocity from the Earth. So they only operation around the Earth atmosphere. Then what about a rocket? Yes, how can a rocket achieve escape velocity from the Earth and send the spacecraft into the outer space? Interesting, right? Okay. So if you look at the GIF or animation there, the launching of rocket requires large quantities of fuel. So this large amount of fuel will produce high thrust that enable the rocket to achieve escape velocity of the Earth. So hence, it can send the spacecraft into the outer space. That simple. Oh, I'm sorry. I thought we are finished. Supposed to be, we have one more learning standard, the fourth one. Okay, now is the solve problem involving the escape velocity for a rocket from the Earth's surface, the Moon's surface, Mars' surface, and the Sun's surface. Okay, let's figure out these problems together. So I hope this animation will boost your interest on this chapter. If you compare, we have 1, 2, 3, 4, 5, 6, 7, 8 planets there, from Mercury on the very left to the Neptune on the right. Okay, can you tell me which one have a highest escape velocity? Look at Jupiter. It gone too fast, only with a blink of eyes, with 134,664 mile per hour. Okay, and which one is the lowest escape velocity? Yeah, you can see the lowest escape velocity here is Mercury, with about 9,507 mile per hour. Okay, so where is Earth? This is Earth. It's about 25,000. 31 mile per hour, equivalent to 11,200 meter per second. Interesting, right? Well, now let us try this fourth activity on practicing to calculate the value of escape velocity of planet. Okay, let us practice this together. So I hope you can take your calculator, apply this equation of V equal to the square root of 2gm divide R. Find the escape velocity for Venus, Mars, and Jupiter. From the information given here, they give you the mass and the radius, so you can find the escape velocity easily. Alright, okay, so what is for Venus? Very good. It is 1.0362 times 10 4 meter per second. Then Mars. Yes, it is 5.0189 times 10 to the power of 3 meter per second. Then Jupiter. Yes, Jupiter has 6.0217 times 10 4 meter per second. Okay, next question, student. Question number 2. We have now moon and a sun, okay, shows in this table with the mass and radius respectively. So first, you have to compare the gravitational acceleration on the moon and the sun. And second, compare the escape velocity from the moon and the sun. So how to make comparison? Yes, through calculations. Okay, let us calculate the gravitational acceleration and escape velocity for both moon and sun. Okay. Okay, we look for the gravitational first. So this is the formula for gravitational acceleration. Remember, we learned this in the first content standard 3.1 earlier. So you can refer back to the video. So G equal to gm divide R squared. And for moon, the gravitational acceleration is about 1.619 meter per second squared. And for sun, it is, yes, 274.006 meter per second squared. So if you compare who has the greater, the moon has a lower gravitational acceleration compared to the sun, or vice versa. You can say the sun has a larger or higher, greater, okay, gravitational acceleration compared to the moon. Alright? Okay, then second, compare the escape velocity. Remember, this is the formula for escape velocity. V equals square root of 2gm divide R. So for the moon, it is 2.3738 times 10 power of 3 meter per second. And for the sun, it is, yes, very good, 6.1759 times 10 power of 5 meter per second. So we can say the moon has a lower escape velocity compared to the sun, and vice versa. The sun has a greater escape velocity compared to the moon. Okay, question 3. Discuss whether escape velocity from Earth for spacecraft Y of mass 1,500 kg is different from spacecraft Z of mass 2,000 kg. So actually in this question, we want to learn either the mass of a spacecraft affect its escape velocity from the Earth's surface. Okay, so student, actually, from our understanding, the escape velocity from the Earth of spacecraft Y and Z is the same, which is 11,200 meter per second. Okay, and here, I want you to clarify that the mass of spacecraft does not affect the escape velocity from the Earth, because the factor that affect the escape velocity from the Earth is the mass of the Earth and the radius of the orbit. Are you still doing good there? I hope so, because we are going to discuss question number 4. Yes, Proba-1 satellite, okay, orbits the Earth at a height of 700 kilometer. So whenever you see this word at a height of 700 kilometer, so you should understand that to determine the radius of orbit, we have to find the sum of the Earth radius plus the height of the satellite from the Earth surface. Alright? Okay. So this is the formula for linear speed. V equal gm divide R. Okay, R here is R plus H. The orbital radius here determined from the Earth radius plus the height of the satellite from Earth surface. So we do the substitution for G, mass of Earth. This is the Earth radius and the height of the planet from Earth surface. Alright? Okay, so answer 7.5048 10 to the power of 3 meter per second. The linear speed of Prova 1. Okay, student, as our final exercises, let us try to figure out some example of SPM trial question. And now here we have from Kelantan 2022, question 5. Okay, you are given with diagram 5.1. It shows two satellites K and L with equal mass. Highlight the equal mass orbiting the Earth at a height of 542,000 kilometer and 359 kilometer from the center of the Earth respectively. Highlight this from the center of the Earth. What does it mean? Because this one is readily the orbital radius. So you don't have to add with Earth radius anymore because it is stated this height is readily from the center of the Earth. Okay, the second information, it says that the satellite are orbiting at a linear speed in the same direction as the Earth rotation, but has different orbital period compared to Earth. So whenever they have different orbital periods, so we understand K and L is, yes, it's a non-geostationary satellite. Even though they're orbiting with the same direction as the Earth rotation, but they have different orbital period. So that's why they are non-geostationary satellite. Okay, this is the reason for you to take note. Alright, okay. Okay, second question, question B. Okay, now we have to make comparison. We observe satellite K and L, and you have to compare the distance from the center of the Earth. So you can compare which one. So distance from the center of the Earth of the K is greater compared to L. So you can write satellite K greater than satellite L or vice versa. Satellite L less than satellite K. And for the magnitude of gravitational force, yeah, so we understand that magnitude of gravitational force acting on satellite L is greater compared to satellite K. Remember, magnitude of gravitational force is inversely proportional to the radius of orbit. Yes, very good. So when the radius of orbit is lower, the gravitational force will be greater. Yes. Okay, and what about the linear speed? Linear speed. Okay, so yes, linear speed of satellite L is greater than satellite K. Yes. Okay, then C, based on our answer, you have to state the relationship between magnitude of gravitational force and distance from the center. So how do we relate them? Very good. So we can say magnitude of gravitational force acting on the satellite increases. So the distance from the center of the Earth decreases. They are inversely proportional. And to the linear speed, yes, it is directly proportional. When the magnitude of gravitational force acting on the satellite increases, linear speed of the satellite increases. Okay? Okay, next. Okay, this is an application. What do you think will happen to the motion of both satellites if there is no gravitational force acting on them? So this one we can relate to the hammer throw event. What happened to the hammer if it is released from the athlete's hand? So we say the satellite will move away from the Earth in a straight line, or you can say the satellite move away out from the orbit. The satellite will be out from the orbit. Okay, similar to this case. Okay, as in a hammer throw, when the string was released, where there is no force longer acting, the hammer will move in a straight line, tangent to a point where it is released. Okay. our last question. Let us try to look at one long essay question. Okay, you are given a communication satellite. Okay, communication satellite with a solar cell and antenna as shown in diagram 9.2. Alright? Okay. So this is the table, shows characteristic of 4 telecommunication satellite. You are given with J, K, L, and M with 4 characteristic. The size of the antenna, either large or small. That is our choice. The type of satellite, geostationary or non-geostationary. The number of solar cell, better to be more, better to be moderate, or better to be less. And the mass, better to be high or better to be low. So what is your task? To choose the most suitable satellite and to justify your choice. So remember the techniques I always tell you, so you can apply peak to peak here. So we tick first. The size of antenna, large or small. The type of satellite, better to be geo or non-geo. Remember telecommunication satellite, what type? And the number of solar cells. So after that, we put our selection in table. Okay, the first characteristic, large antenna. Why? So it can reflect more wave. Okay, mean it can send more signal. Second, the type of satellite must be geostationary. Communication satellite is a geostationary. So this is the reason. So it will be always above the same geographical location on Earth. Or you can say so that the direction of motion is same as the direction of the Earth rotation. And the third characteristic, the number of solar cell is better to be more, so that it will collect more light energy. And the fourth characteristic, the mass should be low or small. Remember, never write the number 800 kg, 200, just write low or small mass. So it will have a high acceleration. This is from the Newton's second law of motion formula. When the mass is small or low, the acceleration will be higher. So other than that, you can write, so it consumes less fuel during launching. So by this, we choose satellite J. Why? Because it has large antenna, a geostationary satellite, it has more number of solar cell and low mass. Alright, student, I guess we have come to the end of this lesson. So what do you think of 3.3 man-made satellite? Easy, right? Yes. So thank you very much for joining me in this video. So I hope to see you again soon in the next chapter, chapter 4, heat. So thank you again. Take a good care of yourself and Assalamualaikum. Jumpa lagi.